Hi, this is Mr. Blay here. We are talking today, or kind of continuing on today, with trigonometric functions. Specifically, what we're looking at today is a composition of two trigonometric functions. So it's basically when you're putting two functions together. Specifically, the ones we're going to focus on are inverses and the original function. Okay, so again, you can follow along in the notes that I've also posted. Okay, so for this here, okay, one of the things to consider, we've done composite functions before. So composite functions, remember, these are things like f of g of x. That's a composite function. Could also be written as f of g of x. Okay. Either way, with composite functions, you're basically plugging in one function into the other. Okay. One thing to remember about composite functions, when you take a function and plug it in to its inverse, both of the functions cancel out and you just get x. Okay. So again, in practice, this works over here. This is a really good example. So let's say the original function is x squared. If you plug that into its inverse, which is the square root of x, both the squared and the square root cancel out. So you just get x. Okay. This also works if you take the inverse and plug the inverse into the function. You can plug it in either way. An inverse and its original function, when you plug them into each other, they cancel out to the variable x. Okay. So this is going to be very helpful when we're doing tans of inverse tangents or sines of inverse sines, whatever it might be, okay, because ultimately the two functions will cancel out for us. However, when you're doing this, what you're left over with is very important to understand domain restrictions that you have to consider. So if you look at the next slide, okay, this is some of the domain restrictions for the originals and the inverses. Okay, this is also in your textbook as well. These originals over here, these are the domains that we have. Okay, so this is sine, cosine, and tangent. This is the actual domain of sine, domain of cosine, and domain of tangent. You can see tangent really has no limit to its domain. But tangent is the only one that doesn't have a limit. Sine and cosine, they're both limited to -1 to 1. Okay, and so that's very limited. You can only get numbers in between -1 and 1. And if you look around the unit circle and all the points in the unit circle, you can see like your square root of 2 over 2, your half, your square root of 3 over 2. They're all between -1 and 1. That's its limited domain. On the other side of things, especially if you watch the other video, these are the inverse domains. We talked about these in the previous video. So the inverse domains are limited from -pi over 2 to pi over 2, and that's true for sine and for tangent here. The main thing with both of these, okay, is again, notice there's no equal to down here. Okay? For tangent, pi over 2 and -pi over 2 don't actually exist, but for sine they do. Okay? Cosine's a little different, it goes from 0 to pi. Okay, so again, remember these domains, and I'll show you how this works in these couple examples. So here's our first couple examples. These are very nice and easy. Okay? And actually, I know on your slides you can actually see the answers, but I will take these answers away. Okay? So the first one that you see here, this is sine, and then you have sine of inverse sine of -1/4. Okay? So as we said in the previous example, okay, when you have a sine and an inverse sine, okay, these two things right here, when you plug them into each other, the sines actually cancel out. Because sine of inverse sine is nothing. So you just get -1/4. Okay? So the only thing you have to keep in mind here to determine whether or not your answer is right or if you need to change it, what you need to think about is the domain of the sine function. Okay, now notice I said domain of sine, not inverse sine, because I'm always looking at what is furthest out. In other words, what are we plugging into? Okay, here, this whole bracketed idea is being plugged into sine, so I need to think, what's the domain of sine? Now, the domain of sine is somewhere between 1 and -1, which means this is okay. All right, this is an okay answer that works. It fits in that domain, and we can keep it. Okay, so arctangent of tan. All right, now again, those are inverses. So since you're plugging the original tangent into arctangent, these cancel out. So you then just are left with pi over 2. Okay, so let's now think about what is the domain of inverse tan, okay, or arctan. Okay, so the domain of this is from negative pi over 2 to positive pi over 2, okay, and x is there. Now again, I got this from the previous slide, okay, or you can have it memorized, whatever you want to do. But you can see that this pi over 2 is not included in the domain. Therefore, this has no solution. Okay, this actually does not have an answer because this number, pi over 2, that doesn't actually fit in the domain of tangent. Okay, so then if you continue on to arcsine of sine, again, since these are inverses of each other, they cancel out. Okay, so you get 7 pi over 4. But now you have to consider what is the domain of arcsine. Okay, because again, you always take the one you're plugging into. So domain of arcsine, okay, is going to be negative pi over 2. It's actually almost the same as the tangent. It's just that these two numbers are included. Okay, so what you need to figure out is 7 pi over 4 is not in that domain. However, okay, can it be written in that domain? Okay, so what I mean by this is 7 pi over 4. Now that's almost 8 pi over 4, which is almost a full circle. Okay, so 7 pi over 4 is right down here. Okay, so obviously to get there, this right there would be 7 pi over 4. Okay, so you're in quadrant 4. Okay, which again, for arcsine, quadrant 4 is legitimate. You just need to figure out how can I get this angle in the domain. And you can do this by using its reference angle, or essentially its sort of counterpart angle, which in this case is negative pi over 4. Okay. Now again, you have to keep it as a negative, okay, because again, this isn't specifically a reference angle. It is an angle of a ratio or inverse ratio, okay? So you actually have to give the true angle. How did I get from the starting initial side to the terminal side? All right, and you had to travel in a negative direction. Okay, so I do have a few more examples. I'm going to do the last couple of examples in a separate video. Okay, if you're feeling pretty comfortable at this point, go ahead and start trying some of the work. If you get stuck again, go reference my second video on evaluating composite functions.